Hi guys, today we're doing an A2 pure paper. Here we go. Okay, first question, exponents. So the first task here is to just rearrange, giving us 3 to the x plus 2 is equal to 8 times 3 to the x minus 16. And then we gather the like terms. So we get that 7 times 3 to the x, which is me taking this over to that side, and take that one over there, gives us 18. And so 3 to the x is equal to 18 on 7. And then we just take a log base 3. So we have log base 3 of 3 to the x is log base 3 of 18 over 7. And you can see that this thing is just equal to x. And then you work that out in your calculator, no problem. Okay, next one is an expansion. So we're looking at a Taylor expansion, because you'll notice that the exponent here is a negative fractional power. So you can't use the binomial expansion or anything like that, because that requires a positive integer power. So the way to do this is to think of what is our function that we're expanding? Well, we're just expanding the second one, because the first one's already expanded in that it's super simple. So our f of x is 1 plus 2x all to the minus 3 halves. So our first derivative is going to be the minus 3 halves comes down, and we get a 2 from inside, and this bracket goes to minus 5 halves. And our second derivative, because we're looking up to terms in x squared, so we're going to need our second derivative for the second derivative term, minus 5 over 2 comes out. So by the way, these two have cancelled. So we get plus 15 over 2 times another 2 has come out. 1 plus 2x to the minus 7 over 2. And then if I just evaluate this at x is equal to 0, all of these guys, the first one, well, we just get 1. The second one will give us minus 3. And the last one will give us plus 15. So this is the procedure. You decide in your function, you work out the derivatives up to whatever order is required, and then you evaluate them at 0. So now we're ready. And our equation for the Taylor expansion is that f of x is about equal to f at 0 plus f prime at 0 times x plus 1 over 2 f prime prime of 0 evaluated at 0 x squared, plus, of course, other terms, but now we only care about these ones. And so in this case, this is equal to 1 plus, minus 3x plus 15 over 2x squared. And now we take this and we multiply it by 2 minus x, and we look for anything up to x squared. So we don't care about the term where this x here multiplies that x squared there, because that'll give us x cubed, and we don't care about that. So let's just multiply this out. The 2 multiplies, we get a 2 minus 6x plus 15x squared. And then this minus x multiplies everything, minus x plus 3x squared, and we don't care about the x cubed term. And this gives us 2 minus 7x plus 18x squared, which is the correct answer. So best to be just careful. Don't try and do it on the fly unless you're super experienced with this. Just write everything out, and then you'll be sure you won't make any mistakes. Okay, question 3. So we're being asked to prove, we're being asked to manipulate some trigonometric functions here. So sec of theta, well, what is that? That's just 1 over the cosine of theta. I'm going to drop the theta. I'm just going to write, cos sec. So 1 over cos, which is the sec, is equal to 3 cos plus tan. And now I'm going to multiply everything by cosine. So I get 1 is equal to 3 cosine squared plus, and using the fact that tan is equal to sine over cosine, multiplying tan by cosine just gives us sine. And then I use the identity that cosine squared plus sine squared is equal to 1. These are all in your formula booklet. I get that this is 3 times 1 minus sine squared plus sine. And this gives me a quadratic equation in sine, which is 3 sine squared of theta minus sine of theta minus 2 is equal to 0. If I solve this, I get that the sine of theta is equal to 1 plus or minus square root of 1 plus 4 times 3 times 2 all over 6, which is 1 plus or minus 5 over 6. So that's either going to be equal to the positive one, which is 1. So you get 6 over 6, or you get minus 4 over 6, which is minus 2/3. So we're looking for the region between where theta is between minus 90 and 90, or minus pi over 2 and pi. So remember that the sine function goes like this, where that's 2 pi, or sorry, 360. This is 180. This is 90. So we only care about this bit, and we care about also the reflected bit over here, minus 90. So we only care about this zone. And so if sine of theta is equal to 1, we get that only once, where therefore theta is equal to 90 degrees, but this is not allowed because you can see that the limit is strictly less than 90. It doesn't include 90. So we don't care about that answer for theta. But if sine of theta is minus 2/3, that happens somewhere over here. And if you put it into your calculator, you get that theta is equal to minus 41.81 degrees. And that is the only answer that satisfies the conditions. So that's them trying to trick you and being a bit sneaky there, not having it's just a strict inequality, not a semi-equality. And you just have to be careful about the ranges that they give you, and you should know the graphs of the functions off by heart. So we've got 2 solutions, and each one of these potentially has, loads of possible values of theta that, in fact, infinitely many which could return them, but we're just given this range in which each one only has 1, and in fact, this guy is not allowed at all. Okay, question 4. We're given this equation of a curve, and we're told that A is a non-zero constant, and we want a point where on this curve where it is parallel, where the tangent or the curve itself is parallel to the x-axis. So the tangent to a curve, for this we need the derivative, and this is equal to, so I'm going to differentiate the whole thing with respect, so I'm going to do what's called implicit differentiation. Remember that if something's parallel to the x-axis, this means that dy dx is equal to 0. So implicit differentiation, I'm going to differentiate the entire thing by x. So this thing, and the right-hand side is just a constant, so it's going to go to 0. So I'm going to, firstly, just to make it simpler for my life, I'm going to multiply this thing out. That's x squared y minus 6xy squared. And this is equal to, and remember that y can depend on x, so you have to use the product rule and the chain rule. So I'm going to first differentiate the x squared part, so that's 2xy. Then I'm going to differentiate the y part, so that's x squared, and then dy dx. So I can just leave it as dy dx. I don't need to know what the dependence of y is. So that's that term dealt with, and the same thing happens to the next term. First we differentiate the x part, and then we differentiate the y part. So you should practice this implicit differentiation, and it really helps you understand really what derivatives are at the end of the day. Now I'm setting dy dx to 0, and this gives 2xy minus 6y squared, and this is equal to 0 because all of this was equal to 0. So this was equal to d dx of a constant, where constant 9a cubed, so which is of course just 0. So I have this relationship. So I'm just going to take a 2y out, and I'm going to get x minus 3y is equal to 0. So I have 2 options here that would satisfy this. Either y is equal to 0, But then you notice that this would mean that this would be x times 0 is equal to 9a cubed. But this means that a must be equal to 0. But this is not allowed because we're told that a is a non-zero constant. So we're not allowed that solution. This happens a lot where you have to throw solutions away because they don't fit what they say. So the only other solution is that x is equal to 3y. Right? So if this is the case, then we return to our original equation. Oh, just so I can show it there. And we plug that in. And we get that 3y squared times minus 3y is equal to, which is equal to minus 9y cubed. And we're saying that this is equal to 9a cubed. So this, of course, means that y is equal to minus a at this point. And that means by this relationship here that x is equal to minus 3a. So the point which satisfies all of these rules is the point minus 3a comma a. Okay, so the important thing to do was the implicit differentiation. And then to recognize that we can set this dy dx to 0. And just remembering that y depends on x. And then realizing that we can throw away a solution and only get 1 point. Okay, question 5. So here we're being asked to prove a trigonometric identity. And these things are just fiddly, but you can always get there in the end. The tricky thing is to be sure that you don't end up going around in a circle, which can be very annoying. So what do we know? We see that we've got a mixture of thetas and 2 thetas as arguments for the function. So the first thing we're going to want to do is expand our the 2 theta. So let's look at the left-hand side. So tan 2 theta is 2 tan theta over 1 minus tan squared theta. And from this, we are subtracting tan of theta. So this is equal to, and I'm going to bring the tan of theta on top of this. I'm going to give them the same denominator. So it's going to be 2 tan theta minus tan theta 1 minus tan squared theta all over 1 minus tan squared. So this is equal to, and if I multiply it out, I realize that this is equal to the tan of theta times 1 plus the tan squared of theta over 1 minus tan squared theta. And recognize that 1 plus tan squared theta is just equal to sec squared theta. So this thing is equal to tan of theta over cosine squared of theta. And then I'm going to put this as 1 minus sine squared theta over cosine squared theta, because that's what tan is. So this is equal to tan of theta over cosine squared theta minus sine squared theta. And if you look in your formula booklet, you'll see that that is exactly the formula for cosine 2 theta, which in cosine is just 1 over sec. So this is tan theta sec 2 theta. So you see it's just mechanical application. And there's really, the important things to remember is that if there's a 2, then you need to expand that and be aware that you might need, and here's a 2 on this side, so you're going to need to draw things out. So you're going to be on the lookout for something that looks like the expansion of sec 2 theta, and you're trying to shape this. And usually you can, if you're really in a tight spot, just make everything in terms of sines and cosines, and then things will cancel that you didn't realize could cancel. Okay, so now we're going to use this information to solve this integral. So obviously this is the same thing that we had on our right-hand side, so we can express that as 0 to pi on 6 of tan of 2 theta minus tan of theta. So now you're going to have to, so firstly I'm going to express this as 2 different integrals, and I'm going to change the limit of integration. So instead of, I'm going to go, this is, so I'm wondering how to do this, that would be the most obvious, but let me define something called phi, and I'm going to call, and this is going to be defined as 2 theta. So if you differentiate, that means that d phi d theta is 2, which means that d theta is equal to 1/2 d phi. And so this is going to be the first term is going to be the tan of phi d phi. And there's going to be a 1/2 coming out because I'm replacing, this is d theta. So d theta has become 1/2 d phi. This is tan of phi, and then the limits will change. So when theta is 0, phi is also 0. But when theta is pi on 6, phi is pi on 3. And then the other one I'm not going to bother doing anything with. This is going to be tan of theta d theta from 0 to pi over 6. Okay, so we've got two integrals. Both of them contain the tangent of the measure, but now we're going to we don't have any formula in our formula booklet for the integral of tan. So I'm going to use the fact that this is the integral of tan of theta d theta is the integral of sine theta over cosine theta d theta, and then I'm going to define an integration variable u, which is defined as cosine theta, and this means that du d theta is minus sine of theta, so that d theta is equal to minus 1 on sine of theta du. This means that this integral is equal to du of sine theta over minus sine theta 1 over u, which is integral du over u minus du over u, which is minus natural log of u. So we're almost there. It's a lot of work for this question, to be honest. You're having to, unless you may well want to memorize the integral of the tangent function. That's probably a lot easier than trying to rederive this in the exam, but they don't give it to you, so it's good to know how to derive it. I'm just making this smaller. So this minus ln u, if I evaluate, this is actually going to be minus ln of, and then u is equal to cosine of theta. So the integral that we're looking at is going to be 1/2 integral of minus ln of cosine of phi between 0 and pi on 3 minus ln of cosine of theta and theta between 0 and pi on 6. And so if we do that, we get the 1/2 minus ln of 1/2 plus ln of 1 plus ln of square root 3 on 2 minus ln of 1. And ln of 1 is just 0 because e to the 0 is equal to 1. 0. So this is ln of square root 3 on 2 minus 1 minus ln of 1/2 to the, actually, you know what, minus ln 1/2 ln of 1/2. And then we realize that this thing is that the square root of 3 on 2 is equal to 3 on 4 to the power of 1/2. And then we bring that 1/2 out. So this is 1/2 ln of 3 on 4 minus ln of 1/2. And then we realize that this is equal to, if you can bring these together, you get 3 over 4 divided by 1/2. So we get 1/2 ln of 3 on 2. Worth going through that yourself in a little more slowly, I'm sure. But this was just applying the rules of logarithms and just being a bit careful. So the tricky bit was deriving the integral of tangent of theta. I mean, that's non-trivial. And you have to sort of know that you have to use substitution. If you want to memorize it, that's perfectly fine too, and maybe worth doing that for the exam. I mean, it's not that bad. The result was that the integral of tan of theta d theta between a and b is equal to minus the natural log of the cosine of theta between a and b. So that is the result that you should memorize if you want to, rather than driving in the exam. That's, to be honest, this is the first time that I've seen that come up in a past paper where they're asking you to just integrate the tangent. So who knows? Okay, so by sketching a suitable pair of graphs, show that this equation has one root in some interval. So we've got cosec of 1/2 x on one side, and we've got some line on the other. So we know that the cosec of 1/2 of x is equal to 1 over the sine of 1/2 x. So here I'm going to graph, firstly, the sine of 1/2 x as a function of x. So when x is equal to, remember that the sine runs from 0 to 2 pi before repeating itself. So when, so it means that 1/2 x is going to be equal to 2 pi, which means x is going to be equal to 4 pi. And here's 2 pi, and here it's pi, and here it's pi on 2. And now what does that mean for the cosine? The cosec? Well, cosec is obviously 1 over sine, and that means that when sine goes to 0, which is here, here, and here, the cosec must go to infinity or minus infinity. So we only care for the interval between 0 and pi, and so that's this section here. So that will look like at 0, at x is equal to 0, the cosec diverges because sine goes to 0, so you're dividing by 0, so you just go up to infinity. Then you come down, and then when the sine is equal to 1, then the cosec is also equal to 1 because 1 divided by 1 is also 1. So at pi, at x is equal to pi, the cosec of 1/2 x is equal to 1. So that's the graph of cosec of 1/2 x. And now we want 1/3 x plus 1. Well, the y-intercept is obviously at 1. And then it heads off with a shallow gradient of 1/3. So you can see that obviously there is only a single crossing over point within this section. So in the next one, we want to show that by calculation that the root lies between these two values. So the key to this is to notice that before the root, so before the root value, cosec of 1/2 x, so the cosec line is greater than 1/3 x plus 1, and after it's less. You see that? So they cross over, therefore, you know, they sort of switch seniority. One dives below the other. So the key to doing this is just to evaluate it, to say that the cosec, so if x is equal to 1.4, then the left-hand side with the cosec is equal to 1.55, and the right-hand side is equal to 1.47. And when x is equal to 1.6, the left-hand side is equal to 1.39, and the right-hand side has gone up and equal to 1.53. So we're happy with this. You can see that the right-hand side is increasing and the left-hand side is decreasing, as in our graph. Okay, so now they're giving us an iterative formula, and they're asking, they're saying that if this converges, what does it converge to? Well, converge So this is something with xn plus 1 in terms of xn. So the way these things work is you start with an xn, you use this to calculate an xn plus 1, then you plug the xn plus 1 where xn was, and you work out xn plus 2, and you get this thing that sort of gets closer and closer. So if it converges, well, that's the same thing as saying that x of n plus 1 is equal to xn. So at some point, your xn, when you plug it in, will give you the same thing out, and that's what convergence means. So you are looking for one where they are the same, and we're just going to call that x. So you're looking for when x is equal to 2 arcsine of 3 over x plus 3. And so 3 over x plus 3 is equal to sine of 1/2 x, and you can see where I'm going with this. You can flip them and get that 1/3 x plus 1 is equal to 1 over sine of 1/2 x, which is cosec of 1/2 x. So we've recovered the original equation. So there you go. That's exactly how you show this. You call both xn plus 1 and xn x. You call them both x, and you rearrange the equation. That's the form of these problems. This last part, they want you to iterate, and this is extremely boring, but you should just practice doing it if you want. As you know, if you're sure if you need practice, really, it's very mechanical. So that's where you just you know that the root is between 1.4 and 1.6. So you're going to want to take maybe 1.5, so use it as your xn, plug it in, write down. So you write that down. You say xn x0 is equal to this. Then you plug in and you get your x1. x1 equals this, and you plug the x1 into the formula and get x2. So you know x0 is equal to 1.5 0 0 0 0. X1 is equal to whatever it is, x2 is equal to whatever it is, blah, blah, blah. And when you get to a point where the first, so you have, 1 point, and then when you get to the point where the first 3 decimal places are not changing, that is convergence. It means it's converged correctly up to the first 3 decimal places. But you still have to give the whole thing as 5 decimal places. Okay, question 7. So this is just integration. And differentiation first, and then integration. So we're given this formula for this curve, and we're told its maximum point is m. So if we're finding the coordinates of m, obviously we're going to have to differentiate, because that's how you find maxima and minima. So dy dx, you just have to use the product rule here. So I'm going to, the first bracket, you differentiate it. You get that 2 minus 2x e to the 1/2 x. And then I'm going to add my, I'm going to differentiate the second part, which is e to the 1/2 x, and that gives 1/2 e to the 1/2 x. And if I just pull these together for later convenience, I get that 2 minus x minus 1/2 x squared e to the 1/2 x. And now I'm going to say that this is equal to 0 at m. So either this bracket is 0 or this exponential is 0, but we know that e to the anything is never equal to 0. The graph of e looks like this. It crosses at 1. It never touches 0, because you can never raise anything to a power and have it be 0. So therefore, it's the bracket which must be 0 in order to satisfy this equation. So we got that 2 minus x minus 1/2 x squared is 0. So that gives us that x squared plus 2x minus 2 is 0. And of course, we use the usual formula. So we have x is equal to minus 2 plus or minus square root of 4 plus 16 over 2, which is minus 1 plus or minus square root 5. Now, obviously, m has a positive x coordinate, as you can see by inspection of the graph. So we know that x is equal to minus 1. X, of m is minus 1 plus the square root of 5. Okay, now they want us to integrate. They want us to find the exact value of the area of the shaded region. So that means integrate, bounded by the curve and the positive x-axis. So we're just going to integrate this between those two values, between 0 and 2. So we've got, we have to use we obviously, if you look at the equation, it doesn't look very amenable to integration. That means we have to use integration by parts because we've got a polynomial and an exponential. The good thing about the exponential and also about, trigonometric functions is that they cycle. And so we can just play with them however we like. They're incredibly easy to integrate and differentiate. And with polynomials, what we want to do is be differentiating those until they're constants. So this is exactly when you would use the integration by parts. So the way I always remember this, I write down that f g prime is equal to f g minus f prime g. And that's what I've got memorized. And whenever I need to use integration by parts, I just write that down, like on my exam paper or wherever, because otherwise I never remember it. It is actually in the formula booklet, but this is worth remembering. So in our case, you see that the one that we want to be differentiating is the polynomial, because it means we'll get rid of powers of x as we integrate by parts. Remember, in the exam papers, you almost always have to integrate twice. But so in our first case, our f that we're going to end up differentiating here, that's going to be equal to 2x minus x squared. And our g prime is our e to the 1/2 x, which means that g is a little quick integration of this to e to the 1/2 x. Okay, we're ready. So this means that our integral is equal to fg, which is 2x minus x squared times 2 e to the 1/2 x. You still have to evaluate this bit between 0 and 2, minus the integral of this thing differentiated, f prime, which is 2 minus 2x, times g, which is 2 e to the 1/2 x. Remember, e to the 1/2 x is g prime. That means that g must be 2 e to the 1/2 x, because if I differentiated this g, I would get that 1/2 would cancel. And we notice that this bit is going to be 0, because when I evaluate it at 2, it's going to be 2 times 2, which is 4, minus 2 squared, which is 4, which is 0. And then if I evaluate it at 0, I get 0 minus 0. So this whole thing is 0. Minus, so I'm going to just separate out this bracket. So it's going to be 2 times 2, which is 4, integral e to the 1/2 x, plus 4 integral x e to the 1/2 x. And the first one of these is minus 4, and then I'm going to integrate this guy, which as we know is 2 e to the 1/2 x between 0 and 2, plus 4, and then now I'm going to do integration by parts again, and my new f is just x, and my g is the same. So this gives me x times 2 e to the 1/2 x between 0 and 2, minus integral of 2 e to the 1/2 x dx. I should be writing dx here all the time. That's just me being terribly sloppy. And so this is us just having done integration by parts again. And in the second time, our new f was x, so f prime was just 1. And so this is equal to minus 8 times e to the 1/2 times 2 is just e. E to the 0 is 1. Plus 4, and then 4e minus 0, minus 4 e to the 1/2 x between 0 and 2. So this is minus 8e plus 8 plus 16e minus 4 times e minus 1. And this should give us, so that's minus 4, minus 12. Okay, I've made a mistake somewhere. So that's 4 times 2, which is 8, minus 8e, plus 8, plus 16e. And then, there was a 4 here already, so this is 16 there. So this should give us, this should give us minus 8e plus 24. Okay, so that was, a bit of an annoying, slightly fiddly integration by parts. And just remembering that e to the 0 is 1 and not 0. Okay, we've got two planes now. And firstly, we need to show that they are perpendicular. And what we're given is their equations, these two guys. So you should know that to get the normal to a plane, you just take the numbers that are in front of the x, y, and z's. You ignore the thing on the other side; it doesn't matter. So you get that the normal to the first guy is 3, 1, minus 1, and the normal to the second guy is 1, minus 1, 2. And I'm taking the dot product between them. So the dot product is 3 minus 1 minus 2, which is equal to 0. That means they are perpendicular because the dot product vanishes. Great. Okay, now they want us to find a vector equation. So this means an equation of the form r is equal to some point on the curve p plus lambda times some point which goes along the curve, along the line. So we're going from 0 to the line. That's the p. That takes us to the line. And then we're going to move up and down the line. So any point which is reached that way will be on the line by definition. So we got these two planes which are perpendicular. So it kind of looks like that, and there's some place they meet, and there is some line. So you know that line obeys both equations. So if we look at the first equation, and we solve for z, we get that z is equal to 3x plus y minus 2. And if we put this into the second equation, we will get that x minus y plus 2 times 3x plus y minus 2 is equal to 3. And we solve this to get 7x plus y minus 7 is equal to 0. So this is the sort of equation of the line in terms of, x's and y's, and just like an equation of a line on a plane. But it doesn't give all the information. So this is the equation of the line in the z-plane. We want something of this form. But it can tell us if a point is on the line. And we can use it to generate points on the line. So that means that when x is equal to 0, that means that y is equal to 7. And then if we plug that back into this equation here, that gives us that z is equal to 5. So we know that the point 0, 7, 5 is on the line. So I'm going to say that I'm going to call this my point P. Now, when y is equal to 0, this gives us that x is equal to 1, and therefore that z is equal to 1 as well. So this means that the point 1, 0, 1 is also on the line. That means that I'm going to call this, v. So that means that v minus, or rather p minus v goes along the line. So it's parallel to the line. So this is going to be our w that we want. So w is going to be equal to p minus v, which is minus 1, 7, 4. So there we have everything we need. We get that r is equal to 0, 7, 5 plus lambda minus 1, 7, 4. So that's the procedure. You find the relationships obeyed by all the points on the line. You use those to generate a couple of points. You use one of them as your initial point, and then you use another one in combination with that to find a vector which goes along the line, and use that as your w. Okay, question 9, complex numbers. So this is all about expressing W as X plus IY. Sorry, yeah, expressing as X plus IY, which means we just need to solve. In fact, this question in particular is actually quite easy because you can just use the formula. You're allowed to use, the formula for roots on complex numbers as well as real numbers. That's absolutely no problem. So if this is my A, this is my 4 is my B, and that's my C, I get that W is equal to minus 4 plus or minus square root of B squared, 16, plus 4, 1 minus 2i, 1 plus 2i. And you should be happy to see that because it's like this is a complex number multiplied by its complex conjugate, which will give you a nice real number. Fantastic. And this is all over 2 times 1 plus 2i. So this is equal to minus 4 plus or minus square root of 16 plus 4. And this is going to be the real part squared plus the imaginary part squared, because it's a complex number times complex conjugate, over 2 times 1 plus 2i. And I don't like having this complex number on the bottom. That's no good to me because I want it in the form of x plus iy. So x is real. X and y are both real. This is the imaginary part, which is I times something real. And that can never happen if you've got i's on the bottom. So I'm going to multiply this by 1 minus 2i over 1 minus 2i, which is, of course, just like multiplying it by 1, so it's allowed. Because I know that this is the complex conjugate of that, and therefore multiplying them is going to give me a real number. So this is going to be minus 4 plus or minus 6, which is what that works out to, because it gets square root of 36, all over 2 times 1 minus 2i over 1 plus 4. And this is going to be this is minus 2 plus or minus 3 over 5 times 1 minus 2i. And if you work this out, this is going to either be equal to 1/5 minus 2/5 I, or the other solution is minus 1 plus 2i. And then we have it. That's them in the correct form. Okay, so they always love these questions, but they give you 2 conditions and ask you to find the section of the Argand plane. That's the real imaginary plane. So the trick to these is to think of complex numbers. So let's say think of complex number x plus iy as a vector xy, just xy, not xiy, xy in the Argand plane, which it kind of is. They're independent, so they're kind of like independent directions in space. So look at this first one. The modulus of z minus 1 plus I, well, I can just think of that as the modulus of the vector xy, which is what I'm going to call z, minus the vector 1, 1. And what does this look like to you? If I said this is always less than or equal to 2, well, if I subtract 2 vectors, or subtract one vector from another, what that means is that I'm looking at a line that runs between those 2 points. So the point x comma y, which is, the point 1, 1, and this complex number, whatever it is always less than 2. Well, or equal to 2. Well, that's a circle, right? So a circle is the locus of all points that are less than or equal to some distance away from the center. So this first condition gives me a circle with the center at 1, 1, and a radius of 2. Oh, I might have limited myself, but there's the radius. That sort of goes there. So this is our horribly drawn circle. But hey. Oh dear. So that's the first condition. Now the second condition, this you should practice thinking of z not just as a vector, but also as this thing, where you've instead of, this is in polar coordinates, so r is the distance and theta is the angle. So in the same way that the xy plane, you can think of it as r and theta. It's completely equivalent to thinking of it as x plus iy. And in fact, if you expand this, you get that this is equal to r sine theta. Oops, silly. Cosine theta plus I sine theta, in exactly the usual way you'd convert between Cartesian and polar. So arg z, in the same way that we look at, that's theta. The argument of z is the theta angle, and this is equal to the inverse tangent of y on x, as in polar coordinates. So that this condition, if we take the tangent of both sides, we get that y on x is greater than or equal to -1 and less than or equal to 1, which is equivalent to saying that y is greater than or equal to -x, but less than or equal to x. And what does that look like? Well, that's going to look like, so when x is equal to 1, y can't be bigger than 1, and it can't be smaller than -1, and so on. So it's like the line y is equal to x and the line y is equal to -x mark out this region. And so the region that we're interested in is the one that satisfies both of them, and that's that region there. Okay, last question. So this is just this is a differential equation, and just a fiddly, annoying integration procedure. So we've got this differential equation, and we're going to firstly separate variables. So we get dx over k x times 4 minus x on the left-hand side is equal to just dt. And now I'm going to express the integrand of this side as I'm going to decompose it into a over x plus b over 4 minus x. And so this is equal to dx, okay, 4a minus 4a plus b minus a x all over x 4 minus x. And so you see this is the decomposition of fractions. You see that this means that b is equal to a, and they're both equal to 1 over 4. So we're trying to integrate geez, this pen is just driving me insane. So what we have is the integral 1 over 4k dx of 1 on x plus 1 on 4 minus x, which looks pretty good to us now. And that's going to be ln of x minus ln of 4 minus x. We're evaluating this and our limits. So we have a couple of options here. We're given two boundary conditions. So what I'm going to do is I'm going to first use one of them as one of my limits. So this is equal to the integral dt between t equals 0, where x is equal to 0.4, and some later time when x is equal to x of t. And then I'm going to, what I could do is use this other boundary condition as the top limit, and then I would get its k straight away. But I'm going to first get an expression for x and k, and then I'm going to plug the other one in manually. This is just to make it sort of simpler from my perspective. So I have 1 on 4k, and I can simplify this as natural log, and I can pull the logs together, x over x 4 minus x. Between 0.4 and x, and this is just equal to t because that's t minus 0. And this is equal to 1 on 4k, and I will get ln of x over 4 minus x minus ln of 0.4 over 3.6, which is equal to 1 on 4k ln of 9x over 4 minus x. And now I'm going to, this is equal to t. So now I'm going to plug in that x of 2 is equal to 2, which is the second boundary condition that they gave us. And this means I've got 1 on 4k, ln of 18 on 2 is equal to 2. This gives me that k is equal to 1 on 8 ln of 9, which is 1 on 8 ln of 3 squared, which is 1 on 4 ln of 3. And that is what we were asked to show. And now they want the value of t when 90% of the area of the field is infected. Well, 90% of 4 square kilometers is 3.6 square kilometers. So my equation that I worked out, I plug in my value for k. I get t is equal to 1 over natural log of 3, natural log of 9x over 4 minus x. And if I plug this into my calculator with x is equal to 3.6, I get this is equal to 4. And there we have it. This I just used the properties of logs a lot and pulled things together to simplify it for myself. I did it in 2 stages. You may find like other ways are more intuitive to you, but that at the end of the day, it's all about just keeping track of your limits correctly. Oh, and this decomposition of fractions. So if you see an integral, which is some product of stuff that you, so it's something like this where you've got some polynomial on the bottom, consider, unless it's obvious to you immediately, consider decomposing it into fractions. Don't waste time trying to think about what this is and how you would get that. This is how you do it. Okay, so I hope that wasn't too fast for you. Sorry, there was quite a lot to fit in. But if you have any questions, please let me know. And I'll see you next time.